This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, welcome to our first lecture for this week on polymers and viscosity. We have a kind of a 2-hour block and then a 1-hour block on Thursday. Welcome back. I hope you had a great break. I hope you enjoyed Amanda's lectures on surfactants. And today we want to pick up on going from small molecules that you add in solution to modify properties like surfactants to bigger molecules, namely polymers. And then after we talk about polymers, we'll be talking about emulsions. So we're actually coming back to particle dispersions, but we thought we'd finish out covering things that modify particles like polymers and how polymers interact with particles, which is really a lot of the goal of today as well. And then we'll touch on emulsions. Hopefully all told up it won't actually be 3 hours of lecture, but we'll do the polymer block and then I'm going to do the emulsion block separately. So this will be the polymer lecture, then we'll do an emulsion lecture. Maybe this one will be an hour and a little, and the other one will be probably an hour. So, and this is not about micelles. You guys have already done that. And we're going to talk about macromolecules. And I am not trying to go over every aspect of polymer physics. What I'm really hoping to do is get to what would feel like a kind of a more applied understanding of polymers. How are they used in products? What's special about their properties? What are some of the key parameters I might want to relate back to that might help me in selecting a polymer if I had to do that commercially? And I will try to talk about fun and interesting things about polymers along the way. My hope is also, though, that you guys will come with some questions and we'll talk about polymers in the consultation session this week as well. All right, so we're going to talk about polymers in solution and on surfaces. We're going to talk about what's the size of a polymer and what on earth is a radius of gyration. Sorry, I'm just trying to have my notes here as well. Then we're going to talk about polymers in surfaces and really how that fits in surface forces. So we've already talked about a lot of different surface forces, and we want to talk about what polymers can do in the surface force landscape and why they're useful. Possibly, hopefully at the end of this, you'll say, wow, polymers, way more useful than electrical double layer in some senses, but not always. And then we're going to talk about viscosity. Now, we're going to start talking about viscosity and flow. And this is only the first part of it. We're going to talk about it in polymers. We're largely going to stick to dilute viscosity, and we're not going to talk about non-Newtonian fluids or rheology really much today. We'll mention their applications at the end. In emulsions, we're going to talk a little bit about flow at the end of it and viscosity there again. And then next week, having danced around the topic of non-Newtonian flow, we're going to talk about it in the context of particle dispersions because it's a really easy framework to understand. And then we'll relate that back to polymers and emulsions because basically, we'll explain that once, but we're not going to do that till next week. But it'll be fun, and I'll have great rheology stories, I promise. Oh, that's right, 2 fingers. So hopefully you'll understand the role of polymers in different surface forces, and then we'll start to understand the ideas around viscosity and why polymers might be important for rheology, which is just non-Newtonian flow. Rheology is not like theology. Rheology is just the flow of things. When they don't, their viscosity isn't constant. And we'll get into that next week some. So let's talk about polymers a little bit. And these are kind of heavy on text. I'm going to probably try to just highlight things. And I will try to keep you awake. This is meant to be qualitative, but there's kind of I'll keep on flagging and why do we care about this as we go through this. So polymers are just long molecules. Right? They can actually be quite long. They can be very high molecular weights, up to 1 million. But because they're long and kind of string-like, you could think of it, if you had a bunch of polymers sitting on a surface, it'd be kind of like a plate of spaghetti, but the spaghetti would be, instead of as long as spaghetti, it'd be as kind of, several meters long for each noodle. So they're long and string-like. Polymers are, of course, polymer is Greek for poly and mer, which means many units. Poly and then mer is for units. And so the monomer is just a repeat unit. And so the number of units is n. And in this little figure, all the little dots are representing repeat units. And so they kind of come together. And because they have a lot of units, they're quite long, they're often quite flexible. The monomers typically have molecular weights of 50 to 100 Daltons. That's grams per mole, which is probably the unit you're more used to. Dalton is an old measurement, but it's a common one still that's reported, particularly for biological polymers like proteins and biomolecules. You'll still see measurements in Daltons and kilodaltons, but it means gram per mole. So the total molecular weight of a polymer, all things being equal, assuming it's monodisperse, and we haven't really talked about characterization, it's just the number of monomer units times the monomer molecular weight. And, typically you wouldn't see a polymer 1,000 smaller than 1,000, but easily you can see molecular weights of 1,000,000. The length of a monomer segment is L. And so if you have a bunch of little monomers and they're all L long, when you add them all up, you get what would be called the contour length. Now that would be the length of the polymer if it was straight out as a long rigid rod. Now, most polymers, because they have so many degrees of freedom in their motion, will actually kind of coil on themselves. So they're not always that case, particularly if we talk about polymers in their different physical states. So the first one is polymers can be in a solvent or solution as a liquid. So polymers dissolve in solutions or a solvent because, and why I say solvent is hydrophobic polymers that are very oily in nature, don't dissolve in water, but they may easily dissolve in an oil. Whereas polymers that are more polar in nature, like polyvinyl alcohol, polyethylene oxide, those polymers dissolve in water and then might be used in products that have water solvents. But you might also want a polymer that dissolves in an oil-based solvent. Some sunscreens are oil-based, some moisturizers are, and some are aqueous-based. So what you want a polymer to dissolve in may depend on the type of polymer. So polymers can dissolve in a solvent. Now, polymers can also dissolve in themselves, and basically it's just a molten polymer liquid. At that point, it's called a polymer melt. And so a lot of polymers are solids at room temperatures, but as you heat them up, they'll melt just like other solids. Now, when polymers melt, become solids, they can crystallize. They can very often they make what are called semi-crystalline solids, where they make sphere-like crystals and a lot of, if without additives, you can tell a polymer is semi-crystalline or crystalline because it might be opaque. Whereas if they don't crystallize because they're randomly ordered and the chains are all squiggled around each other and things, they actually form glassy solids, and those tend to be much more transparent. All right. We're just gonna reset that share because it's stopped seeming to, no, that's not what I wanted to do. Sorry. Okay. Good. Sorry about that. It was only one squiggle I lost. So when polymers are in solution, because of their degree of freedom, how polymers behave in solution depends on how effectively happy they are. And when I say happy or sad, I'm not talking about the mood of a polymer. It doesn't go out and party and go, woohoo, I'm a free coil, I can be random. It's really how the polymer interacts with the solvent. So the molecular interactions with the repeat units, the monomers, and the solvent can determine how it interacts, or it can actually determine its shape. If the polymer is not particularly happy with the solvent and it has somewhat unfavorable interactions with the monomer units and the solvent, for example, it's a polar polymer and a nonpolar liquid, it might actually be quite small in what's called a globular or spherical globular configuration. Many types of polymers can do this. Proteins are notorious for that, like bovine serum album, beta-galactoglobulin are globular proteins, and that's because of all the hydrogen bonding and interactions between the polymer chains gives it a particular structure. A lot of synthetic polymers tend to be kind of random coils, which means they're quite happy interacting with the solvent. In fact, They're just as happy interacting with the solvent as they are interacting with themselves or other monomer units. So they're quite diffuse in their nature, and they kind of had a random walk distribution of their configurations. They have very many of them. And then you can have polymers that are just long and rigid. Because of their molecular structure, they don't want to interact with each other. Maybe they're highly charged, and so if they were to bend near each other, there'd be a lot of charge-charge repulsion. Now, can anybody think of a rigid polymer? Think about it for a second. So I could do Jeopardy and go do, 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 but just to pause to make you think about it. Think about it. Think about it. Think. Hi. All right. I will pop in and out of the video. So the obvious polymer there is DNA because it's actually quite rigid. It's very highly charged, so it's not terribly flexible. It does have a little twist in it when it has two DNA molecules together, but it's actually quite rigid. So before now, why I mentioned shape is I really want to talk a little bit more about the shapes polymers have and preferably relate them to their molecular weight. How many repeat units they have, and what does that mean in terms of what type of molecular weight does a polymer have, because then I'm going to talk about how polymers stick on surfaces. But before we move on to that, you can't talk about polymer repeat units without mentioning some of their chemistry. And so there's lots of different ways to characterize polymers, but I like the one where you say synthetic polymers and biopolymers. So biopolymers and synthetic polymers. And that's really more about their origin, where synthetic polymers are mostly from fossil fuels. And by the way, that is one of the places where we still have a huge dependence on fossil fuels. Even if we didn't need petrol, most of our plastics come from hydrocarbon and fossil fuel feedstocks. So there are polymers that are water-soluble, polyethylene oxide and polyethylene glycol, which is actually the same polymer, just different molecular weights. It's great for depletion forces. It's used in gels, chromatography. It's great for making things flow thicker. It's also used as a stabilizer in a lot of drug delivery and pharmaceuticals. Polyacrylamide, which is used as a plastic, and is also can be used to bond things. Polystyrene. Polystyrene containers. It's used as particles, containers, rigid particles. It's in polymer alloys. Polyimines are in flocculants and paper making. Pluronics are just amazing as surfactants. So pluronics are what are called block copolymers. You can Google it if you want. They actually have mixtures of hydrophobic and hydrophilic monomers in kind of a particular sequence, or blocks of it are hydrophobic and blocks of it are hydrophilic. So a block copolymer like F108, which is a common one in pharmaceuticals, or F127. F108 will have a hydrophobic bit, and then it'll have a hydrophilic bit, and then it'll have another, it has two hydrophilic bits, so this likes water, and that part doesn't like water. And so as a polymer, they're called block copolymers. But as you can see, it ought to sound a little bit like a surfactant because they have hydrophobic and hydrophilic bits. So they are, in fact, amphiphilic. And what's even more interesting is pluronic polymers sort of form something that looks like a micelle. Polystyrene sulfonate is just like polystyrene, but it has a negative charge on each monomer unit. So it's much more highly charged, and it's much more rod-like than regular polystyrene. Also, polystyrene sulfonate, water-soluble. Polystyrene, not really soluble in water. So by adding charge, it can solubilize in water. So biopolymers, we've got DNA, cellulose, which comes from trees. It's got a repeating unit of glucose. Cellulose is very commonly used as a thickener. Also, it's used as an anti-caking agent. We, I think, already talked about cheese and ground cheese, that it's very commonly in there. Starch, again, is a glucose-based one. Now, an interesting thing about cellulose is the countries that grow a lot of trees in the Northern Hemisphere are working an awful lot on creating what's called the bioeconomy, and that's harvesting cellulose and developing and modifying cellulose into other polymers that can actually fill the needs of some of the synthetic polymers and plastics. So if you really want to see about sustainability in polymers, look up bioeconomy. And look at how that goes into cellulose. It's really interesting. And I know a couple of students, that's an E there, have mentioned they're looking at nanocellulose. So you really do want to talk about bioeconomy there and how it's used. You've got gelatin and starch and cellulose. And So you can see those things. Cellulose is used as a thickener, whereas gelatin's used as a gelling agent. Agarose is also used as a gelling agent. We'll get to what the difference of those are kind of towards the end of the lecture. So those are general polymers. I want to talk a little bit about, okay, so how do I talk about how big a polymer is in solution? So a rigid polymer's DNA is just basically a rod. And you can figure out DNA, a rigid polymer is about as long as it's the number of monomer units times the length of each monomer unit. It gives you what's called the contour length. Now, in a freely jointed chain is a chain that can kind of move around. It's an ideal treatment of a polymer chain. It can just bend around as much as it wants because it has a lot of degrees of freedom. And what you can do is you can figure out that, you know, this chain is going to take on a lot of random configurations over time. It actually is a random walk. We can remember Gaussian statistics if you want as well. But what we actually ascribe to a size is something called a radius of gyration. And we're basically allowing, that's if we were to watch this polymer over a long enough time, the radius of gyration will change as the polymer configuration changes. And as that polymer configuration changes, what happens is the radius of gyration is the radius ascribed to that polymer as if it carved out a sphere of that volume. So it's the radius of basically a sphere that polymer would carve out as the volume that polymer would carve out over time as it moved around. And it's kind of its radius if you said, hey, it's a sphere. Now, it's not really a sphere, right? It's a polymer chain, but you could imagine that, clearly we need the video for this. I had a polymer and it was spinning around and all these different possibilities over time. Well, this is a rod, but it would actually carve out kind of a volume equivalent of a sphere if I just watch this move over time. And that's basically what we're doing with a radius of gyration. Now, that radius, of course, off a lot of statistics we're not going into, is proportional to the number of monomer units times the square root. The length of a monomer unit times the square root of a number of monomer units. Now, the number of monomer units is if I take the total molecular weight and if I took the individual monomer unit and multiplied it by the number of monomer units, I get M. So I've just substituted in, I've said, well, N is really M over M naught. And that's what I've substituted in there. So I can actually say the radius of gyration is related to the molecular weight. Or if I wanted to get fancy, I could say, well, the radius of gyration gets bigger with molecular weight, but it's a square root dependence. So it's not a linear relationship. It's on the square root of molecular weight. So the polymer gets bigger, but only by about its square root of the change in molecular weight. Now that's for an ideal polymer. And when I say ideal, is it doesn't care about solvent interactions. It's kind of it doesn't care about how it interacts with solvents, or it doesn't really see on a molecular interaction scale the rest of the polymer. It just is kind of bending around in freedom. If it's non-ideal and it actually starts to notice the solvent around it and it has molecular interactions with the solvent, you get something called the Flory radius, which is just the radius of gyration with a fudge factor to say, hey, I'm interacting with the solvent. And by the way, there's the ideal case if alpha, this intermolecular expansion factor. So that's how much the polymer can expand or contract based on its interactions with the solvent. An ideal one, the Flory radius, is just the radius of gyration. Now, this is actually called a theta solvent. It's kind of the ideal solvent, and that's the one here where it takes on a random coil. Now, good and bad, these are very peculiar terms. They actually are in the polymer literature this way, but it's really weird in science to say it's a good thing or a bad thing on a quantitative scale. So in a good solvent, the polymer is actually happier to be in the solvent than it would be if it was in a polymer melt of all of the same polymers. So it has a very positive interaction with the solvent, and it's expanded, and it's actually a little bit bigger, and so that's what a good solvent would be. A bad solvent means that there's unfavorable molecular interactions with the polymer and the solvent. It would actually prefer to interact with the other polymer monomer units as opposed to the solvent. So it tries to minimize its area and it becomes globular. And so if you have specific interactions between the monomers, like hydrogen bonding, which is very common in proteins and gives it a lot of their structure, you'll see a more globular nature. And this is sometimes called a poor or bad solvent. So the size of the, excuse me, the size of the molecule is dependent on the molecular weight as well as the conditions of how it interacts with the solvent. And that's actually kind of important, particularly when we get to formulation. Now, I have a little example here we had to do some type of calculation to wake you guys up. If I have a polymer that's got a 10 million Daltons or grams per mole molecular weight, L is 1 nanometer, which is not atypical for the size of a monomer unit, and there's 200 monomers there. Sorry, and the monomer molecular weight is 200, so it's a really bulky, big monomer unit. What is N, LC, and RG? And so those things you should be able to calculate using the formulas above or the ones over on the right. So do take a second, pause the video, and actually calculate something. Otherwise, this lecture will feel not nearly as much fun. To say, gosh, I'll give you a funny picture to look at while you're pausing the video. We'll do this. So you can pause the video with something there on the video as well. So we'll do this. Look, a huge R2-D2. Isn't that a great thing to pause on, or at least in the video screen? R2-D2 is now as large as my head. Okay, I've assumed you paused the video on a large R2-D2 the same size as my head, and now you're back going, gosh, did I get the answer right? And so the N is just 10 to the 6 divided by 200. That's going to be 5,000. LC is just going to be 5,000 times 1, so that's 5,000 nanometers. So think about that as a polymer aspect ratio for a second. It's 1 nanometer wide and 5,000 nanometers long. So it's 5 microns long and only 1 nanometer wide. That's the aspect ratio we're physically talking about sometimes with a polymer. And if you do the calculation, you'll find RG using N or M naught and over M naught. You can calculate it either way, is about 29 nanometers. So the full contour length is 5,000 nanometers, but its average kind of size based on its random distribution of all the monomer segments and its ability to move around in solution is 29 nanometers, but its full contour length is 5,000. So you can see polymers, that's kind of their time averaged random walk, would be a much smaller thing. Now, you could calculate the volume of an object carved out by a 29 nanometer radius, but because the polymer has so much free solvent in between that, right? It's just a string. There's actually a lot of void in that sphere. If you were to say, hey, I have a sphere of 29 nanometers, there's a lot of void there that doesn't include polymer. And in fact, if you say, oh, I have a radius of gyration and I could think of the polymer as a sphere, only about 10% of it's actually polymer. The rest is solvent. So polymers in solution can be quite diffuse. Now that's in an ideal solvent, and that was for 1,000 segments, but a globular protein would have a much higher volume fraction or a much higher fraction of polymer there instead of solvent. But polymers themselves and these random coil configurations can be quite diffuse. Oh, that's the answer without my handwriting. All right, so that's how polymers, and so radius of gyration and what the Flory radius is, we kind of expect you guys to know is ways to talk about when a polymer is in, how do you talk about its size, its radius of gyration, and knowing that the things that affect its size are its molecular weight and whether or not it has favorable or unfavorable interactions with its solvent. Now, we'll talk about ways to manipulate that, or what are some actual, design parameters if I was going to engineer a product that I might like to change the solvent quality. But in the bulk, when polymers are dissolved, they can change their size based on how they interact with the solvent and the molecular weight. What happens when I put a polymer on a surface? For example, I want to coat it on a particle. So if I think about polymers at interfaces, the first thing I have to think about is, how do I get a polymer to an interface in the first place? Well, it will get there one of two ways. You can either chemically graft it, which is what's been done here, where you might end graft a polymer. It might have a functional group that will stick to the polymer surface, or polymers will just physically absorb. And those are molecular interactions. They have them with the solvents, but they also have molecular interactions with solids. And those can be actually they can be a type of van der Waals interaction, they could be hydrogen bonding, they could be charge interactions, but you can get molecular interactions that are attractive between a polymer and a surface as well. And that is called physisorbed. If it's covalently bound, it might be called chemisorbed. And so that's two different ways to get polymers there. Very commonly, chemisorbed is great because you can end anchor it. You can just control, the polymer might have one contact point. Physisorbed means the polymer moves around, it has a lot of loops and trains, and it'll have multiple contact points, most likely with the surface. And so there's two different ways you can stick to a surface. And then depending on how many polymers are on the surface, their configuration will change a little bit. Sorry. And so their density on the surface will affect their configuration. Basically, if a polymer is spread out and it's not really bumping into its other neighbors, largely its size on the surface is roughly equal to its size of what it would be in solution. Sure, it's a little bit perturbed by the fact it's stuck to a surface, but roughly its radius of gyration would be the same, would be about the size of the polymer and about how far it's sticking out from the surface. And, if it's in a great solvent, it would be, the Flory radius would be bigger. But basically, if it's stuck on a surface and it's a low density coverage where the polymers aren't really bumping into each other, its dimensions are largely controlled by its radius of gyration. And that will, of course, depend, it's affected by whether or not it's in a theta solvent or a good solvent or a poor solvent. But if you get the graphing density higher, and this can be done in a couple different ways, it can be done with controlled absorption or chemical growth of polymers off surfaces. When the polymers now are so close together that if they were going to occupy the radius of gyration, they're actually going to start bumping into each other, they actually get confined. And when that happens, instead of kind of being what's often called a mushroom shape, this sort of looks like a mushroom, that the polymers doesn't go near the surface and then kind of hangs out up here, but it's kind of blobbish in its nature. These things start to end up as coils that get pushed out from the surface, and they're actually longer. And so then that brush length is not really related to the radius of gyration nearly as strongly. Certainly the molecular weight will affect the polymer brush length, but what will also affect it is the distance between contacts. This is referred to as S. And so that the distance between contacts can also be related to the number of polymer molecules you have on a surface. That's called its surface coverage, and it's defined as 1 over the area occupied per absorbed molecule, or 1 over S squared in odd units. But forming a polymer brush is a very dense layer on a surface where effectively if another molecule or polymer is going to come up to this surface, this polymer brush, it wouldn't see the underlying surface. It would chemically just see the brush. And so when you get this type of coating, when you get a polymer brush on a surface, you actually have a reasonably good coating protecting or isolating the surface from the solvent or from other objects in solution. Now, that can become useful from a force sense. And so now that we've got polymer brushes on surfaces, what happens if I have two surfaces with a nice big coating of a polymer brush and I bring them together? And so what happens is we get a different type of surface force, and it's called a steric force or steric stabilization. And why I care about this is, let's talk about something. Has anyone noticed when we were talking about electrical double layer and stability theory, and we all loved those stability theory calculations and calculating time to first collision, and we noticed that as we added salt, the electrical double layer force screened. In fact, I might ask you what screening is at some point, but is it screens? It gets shorter in length, and you go, okay, what happens to the electrical double layer force as we add salt? It gets smaller and smaller, and then our stability goes away. So the electrical double layer force, great at providing repulsion, unless it's salt. Now, unless you have salt in solution. Now, the problem with that is most biological fluids have around 150 millimolar saline in them. That's salt water, that's what's in blood. And so there's a lot of scenarios where you do have salty water. And so if we design products or particles and want them to stay stable, we may not be able to use electrical double layer, particularly in most biological processes. But polymers are not like polymer coatings don't really care if there's a little bit of salt in the water. If you add excessive amounts of salt, like molar quantities of salt, some polymers may care, but you can actually add an awful lot of salt into a solution and you'll still have a polymer coating. And that polymer coating, when you bring it together, so if I have polymers that are far together and I bring them close together, I'm going to get a repulsive force between them. And this is a steric stabilization force where the polymer brush, as it comes together, overlaps and starts to bump into each other. And because that's, from a molecular energetic standpoint, unfavorable, they push back on each other and you get a repulsive force. And a steric coating is not affected by salt, or not greatly affected by salt. So it's a way to get a repulsive force that's not so sensitive to the background electrolyte concentration. I'm going to turn the video off for a second. And so the mechanisms for steric repulsion are basically saying if I bring two particles together, I've got each particle is coated with a nice coating high brush coverage of a polymer layer. Now the thickness of that brush I'm going to call delta instead of L, but it's still just the thickness. And they're far apart. And then as I bring them together, how I characterize the two polymers, particles, is how far apart is the base of the coating. So S naught is just the distance between where the polymer coating meets the particle. So it's the distance between the bare particles. So why do I get this repulsion? What does it come from? What's its origins? And so it actually comes from the fact that as these two polymers overlap, now I've taken out the polymer brush. I've just kind of drawn the boundary where the brushes would be if they weren't perturbed. As I bring them two together, I have an overlap region, and I'm going to actually kind of draw that out. I've got a region, it's kind of a lens shape, where the two polymer brushes are overlapping in this region. And energetically, it is not overjoyed by that. And that's because the concentration of polymer in this red lens region is higher than the concentration of polymer anywhere else in the brush. And you're getting an osmotic repulsion. This is also, you could think of as an enthalpic effect from the fact that these chains are starting to overlap. There's steric hindrance because these molecules are pushing against each other. And this is particularly when the brushes start to overlap initially, where maybe they're between two brush thicknesses away to one brush thickness away, so delta to 2 delta. You get this osmotic repulsion. Now, when you really start to push these two brushes together and you have an awful lot of overlap, you're now causing these brushes to not just overlap and be uncomfortable, you're causing the whole brush to you push it together so much, it actually has an elastic recoil because it is not overjoyed about the entropic configuration that's happened here. You've really removed the amount of disorder it can have, and you're getting an entropic pushback or an elastic recoil that's trying to push the two polymer coatings apart. In fact, to get to this stage where you have when your separations are much less than one brush, is not going to happen from just particle collisions in Brownian motion. You're going to need flow, or you're going to need to be squeezing particles together. At this stage, you're really trying to push these two particles together much more than they probably would come together if they were in a particle dispersion in nature. So as the polymers overlap, the osmotic pressure increases, pushing the polymer coatings apart. At closer separations, you get an elastic recoil due to the deformation of the polymer. You're starting to bend the polymer chains, they're bumping into each other, and energetically, this is unfavorable. And so there's this very strong restoring force to remove the polymer. Now, the great advantage to this is you're creating a very strong and robust force. And this is a surface force. It doesn't really care about electrolyte. And the polymer coating, when polymers adsorb, particularly at high molecular weights, they tend to stay there for a long time because they have many, many contact points if they're physisorbed, and they don't desorb easily because they're stuck on the surface at so many points. So it's a very effective way to make stable particle suspensions. The challenge is if you make a stable particle to suspension, it normally will not become unstable. It's much more difficult to make them unstable. There are a few tricks though. So there is a steric force law. So instead of, before we had used V for my potential energies, I'm just using phi here, but it's the same ones. we could say, well, we have VT, V steric, and V van der Waals. So there are force laws for steric forces, and there's lots of different force laws for steric forces. It depends. This is kind of for a weaker overlap in kind of the S naught is 2 del to del. This is a force law, and what you can see is the things it's a function of is the brush layer thickness, delta, the radius of the particle, the separation distance, the amount of polymer that's on the surface, that's effectively what C2 is, and B2, which is something called the second virial coefficient, which is basically describing how whether or not the polymer likes to interact with itself. And what you're able to do is you can calculate a steric force law that's effectively a function of S naught. Before we're using H, but I've got S naught in here, and I've also got, in this case, a van der Waals force where H is equal to S naught plus 2 delta. So I've got I've got an expression for potential energy again, and it's also additive. So it's just like an electrical double layer and a van der Waals force. You can add a steric force there, and it's kind of like van der Waals. But the steric force character is a little different. The steric force, and I'm actually going to highlight it here. The steric force is, this is just an illustrative example. The steric force is the green line, right? Well, at 2 delta, hang on, maybe we'll do that in a different color. Do it in pink. The steric force is very high and it drops down. And then when 2 delta, you get to the point of 2 delta where the force, the brushes don't overlap, the force just goes to 0. So it's 0, and as they start to overlap, it increases, and it actually increases basically exponentially. That's roughly what it'll be. So when you add the steric force onto the net force, and we'll do this one in bright green, you get a net force which is repulsive. It may be a little bit attractive because as soon as the brush drops, you get a minimum, and then the van der Waals force dominates out here. But the van der Waals force is not accessed, and you don't see any of the van der Waals force in this region. You don't see that at all. And so a steric force is very good at suppressing a van der Waals force because at short separations, it really grows quickly. It becomes very strong and very highly repulsive. So it's good at stabilizing against a van der Waals force. And in fact, in practice, and so that's the interest of it in a surface forces term. I could give you this type of surface force law, but if I gave it to you, I would give you the equations and I could give you the parameters and I'd make sure the units work. But I could say, hey, you could do a stability calculation here. But what would basically happen is if you had a well-chosen steric stabilizer and you did a stability calculation, it would be millions of years. There are some great gold sols in the British Museum. They're in Rutherford's lab, in Faraday's lab. They're gold particles that were citrate stabilized, and so they had a charge on them and a van der Waals force. And if you calculate the stability, they should be stable for 1,000 years. And so they're still stable today, and Faraday put them in his lab over 150 years ago. I think it's about 150 years ago. And these gold dispersions are still stable. But the real reason they're stable is he added a little bit of guar gum, so they're sterically stabilized. But if I was going to choose a steric stabilizer, what are the properties? What makes a good steric stabilizer? I said if you had a good one, you'll have stability in your particle stirring for thousands of years. So normally 10 or 25% of the monomer units actually stick to the surface. And so some need to stick to the surface, but the rest need to go out. So if you have loops and trains, you can have multiple contact points, but the brush has to be sticking out from the surface. The total absorbed amounts aren't that high. They're 1 to 10 milligrams per meter squared. One really key thing is to get a decent steric stabilized brush so that the monomer is actually sticking out. You need a molecular weight that's typically over 3,000. So to get a really good sterically stabilized system, you need kind of a molecular weight of over 3,000. And it needs to be it doesn't have to be in a good solvent, but it's awfully helpful if it's in a theta solvent. So it's in at least a random or expanded phase. Typically, the concentration you have to put in the bulk to get it to cover the surface is around 1,000 to 10,000 ppm. So the more polymer you get in, the better coverage you get on the surface. The trade-off there is the more polymer that you put in, the higher the viscosity of the solution becomes. And also the polymer tends to be expensive compared to water. And so you want to put as much polymer in as you need to get a good coverage on the surface, but you do not want to put so much polymer in that you're wasting it. And then the other thing is, if you have the ability to measure the thickness of the polymer coating, and there are ways to do that, and you'll hear about them in the characterization methods, basically you want delta to be kind of greater than or equal to 10 nanometers. And where that 10 comes from, why you want delta to be that big, is if the coating is about 10 nanometers or bigger, the underlying particles really don't feel any van der Waals force. After 10 nanometers of separation, the van der Waals force from a surface has really mostly died off. It hasn't completely, but very much so. So you could imagine if you had two 10 nanometer or bigger polymer coatings or brushes on two surfaces and you brought those particles together, they may never come closer than 10, 15 nanometers in separation. So the van der Waals force really isn't going to come into play. So in practical terms, you worry about molecular weight concentration in the bowl, and have you coated the polymer with a thick enough layer to prevent van der Waals forces from causing flocculation. And if you do that right, you will have stable suspensions for years. In fact, there are many processing problems where you have a polymer contamination where you want a system to flocculate, and because you have polymers in it, it won't. One of the examples of this is wastewater treatment, where you have a lot of dissolved particulate solids, and they're stabilized by biological polymers, and so no matter how long you let them settle, they never flocculate because they're so stable from steric stabilization. So steric stabilization, great when you want it, terrible when you don't. So steric stabilization is a very awesome way to have a repulsive interaction between particles. But polymers don't stop there. They can also give you attractive interactions. There are a couple different ways to do it. I'm going to talk about the most difficult one first. As I said, steric stabilization is fantastic at keeping particles from sticking together. You can occasionally, with steric stabilization, if you change the solvent quality, you can cause them to stick. And so if I change the solvent quality from a theta solvent or a good solvent in the bulk, what happens to the polymer in the bulk is it goes from an expanded conformation to this really small globular conformation. And what's happening there is I've changed the solvent polymer interaction somehow so that the polymer prefers to interact with itself than it does with the solvent. If I take a polymer that's on a surface and do the same thing and change the solvent quality, the polymer will want to interact more with itself than the solvent, and it will collapse. Now, when it collapses, two things happen. First, it gets a lot thinner. So if L gets below 10, the van der Waals force that might interact between this surface and another surface could come into play. But additionally, when we collapse it, if the polymer doesn't want to interact with the solvent, it wants to interact with itself, if you bring another coating of a collapsed polymer together, effectively those two polymer brushes are sticky, and they may stick together. Now, to do this, though, is not normally easy. So what are some of the things that might change solvent quality? So let's talk just for a moment what types of interactions do polymer monomers interact with solvent? So on a molecular level, we could have hydrogen bonding. We could have hydration. We could have weaker kind of van der Waals or dipole interactions. But those tend to be weaker. And so let's talk about this in the context example for water-soluble polymer, polyethylene oxide. It's water-soluble. It's we'll skim back to get the molecular structure because we actually care about that for a second. It's got 2 carbons and an ether group, and then just repeats the 2 carbons and an ether group and goes on and does that. And so the oxygens want to interact with the lone pairs on the water. So, sorry, let me go back to where we were. So polyethylene oxide, it has C2H2, C2H2, and an oxygen group, and that's its monomer that it repeats. Well, here, water, H2OH, will actually want to interact with that oxygen group. And so you can get hydration or hydrogen bonding. And so polyethylene oxide is actually quite happy in water. So if I wanted to change the solvent quality to cause polyethylene oxide to become more globular, I could do things like adding alcohol or adding isopropyl alcohol even, something that's miscible with water but would break up its hydrogen bonding. That could cause it to reduce its solvent quality. So I could change the hydrogen bonding in the solvent. I could also remove the amount of free water. If I add a little bit of salt, the polymer won't care. But if I add so much salt, 1 molar or 2 molar, I start to bind up all the free water, and it's all hydrated in the salt. And so a lot of the water can't hydrate the molecule anymore, and that can cause things to collapse as well. So if I change how the polymer is hydrated, how the solvent molecules are interacting, because I put so much salt in the water, I don't have enough free water solvent around to interact with the polymer, that would be a way to cause it to crash out of solution. That actually is very well known for proteins. To get proteins to come out of solution, there's something called salting out a protein. By adding so much salt in the water, the proteins then aren't hydrated anymore, and they become very globular and precipitate out. If I want to affect hydrogen bonding or hydration of solvents to a molecule, one of the other easy things I can do is change temperature. So change temperature. If I heat things up, a lot of polymers will crash out of solution. And so I could change the solvent quality, and these are ways to do it. I could also add things that might affect the solvent structure as well, like ethanol, or depending on the polymer, urea is a good one to add. If I have a polymer dissolved in oil, adding a little bit of water, adding a more polar oil to it would have the same effect. And so I could change solvent quality, and that's one way to do things. It's a bit extreme, but it can be used. And there's problems where, this becomes a problem if you have something where you're trying to you want to break the steric stabilization. You might actually start thinking about this. Sometimes though, people actually want polymer brushes that are very robust in high salt conditions, particularly if you're trying to put particles or keep particles stable in things like reservoirs or high salinity oil recovery. You actually might want things to be stable. But changing solvent quality, changing hydrogen bonding, the polarity of the solvent, its dipole moment, changing temperature, adding salt are all things that can change the solvent quality. For molecules that have acid-base groups on them, a lot of proteins, remember, proteins are made of amino acids. Just by changing the charge state on the polymer, by changing the pH. So for proteins in particular, if you change the pH, you can affect the solvent quality as well. Blue. Don't know why it's doing that. I'll connect for the cable for the next lecture. All right. Right, change pH. All right, so let's try to finish up our discussion on polymer forces. So we talked about, I don't know why I have a double there on that, but anyway. An additional one is polymer flocculation. This is if I have a very low coverage of polymer. I basically am taking a sticky string and bridging it between two particles. And so it will stick on both particles, and it'll eventually stick more on them and cause them to stick together and form a flock. Basically, this works when the distance between the particles is less than the contour length of the polymer. So it's got to be closer than the contour length of the polymer, and it will cause particles to stick together. So if bridging is actually very common in water treatment, when you use polymers for water treatment, this is what they do, is they'll add polymers to flocculate things. And so if you think about a polymer that makes a good bridging agent, it has to have a favorable binding energy for the polymer with the particle. It needs to want to stick from it from hydrogen bonding, ionic interactions. Maybe it's slightly hydrophobic and the particle is. It has to have some match in polarity or really want to stick to that particle. Also, it's used in minerals processing a great deal as well. You want it to be able to stick to the particle, and you want to do that at a low dosing concentration. If it's too high, you'll end up starting to sterically stabilize your particles. And the other thing is you want a long contour length. So you want a high molecular weight. And since you're at a low concentration, you don't have to worry about viscosity. And so if you're doing water treatment, you want water-soluble particles. If you're trying to recover, I don't know, particulates out of industrial fluid, machine fluids where they're oil-based or engine oil, then you'd want a oil-soluble polymer. And so flocculation, it's something to remember. It's not terribly sophisticated in the interaction energy you can describe. There are ways to go into it in more detail, but it's basically, it sticks to both particles. It sticks to particles, and you're doing it at a low surface coverage. And so the final way to get polymers to cause particles to stick together is to have them not adsorb to the surface. So if you have polymers that don't absorb, or not absorbing polymers to a particle, you get a different type of thermodynamic force called a depletion force. And what's happening here is it's another lens. And I'll try to draw the lens. The lens is here. It's again an overlap of two layers. But the lens now is a region not where there's an overlap of polymer, but now it's a region where there's an exclusion of polymer because of the fact that the polymer can't get too close to the surface because it'll bump into the surface. And as these two distances start to get about the same size of the polymer, where that's maybe just its radius of gyration, when you start to get down around the size of the radius of gyration, or about twice the size of the radius of gyration, the polymer can't diffuse into this gap anymore. And if the polymer can't get into this gap, what happens is the polymer can't get into the gap. It's actually geometrically excluded from going between those surfaces. And when that happens, you get what's called an osmotic pressure difference. So this is the same osmotic pressure that you might have thought of about osmosis or reverse osmosis to filters. An osmotic pressure difference is just basically a local difference in concentration in solution. And so if you think about the concentration of the polymer out here is going to be different than the concentration of polymer in the gap. And so that osmotic pressure difference drives an attractive force where thermodynamically you want to remove that concentration difference. And since the polymer can't get in there, the way to remove that concentration difference, if the polymer can't get into between the surface, the way to remove the concentration difference is just to have the particles stick together, because then that osmotic pressure or that gradient in concentration is gone. All right. And so there's a very similar looking depletion force model, because it also works on this kind of lens geometric approximation, where this is a little different than the steric force, that it's now governed by the radius of gyration and the area, and now it's governed by the bulk concentration. This term is actually the osmotic pressure. So that's the osmotic pressure of the solution, is where N2 is the number concentration of polymer, and Kb are just the Boltzmann constant and temperature. So the aspects of depletion that are important or interesting is the bigger the depletion force you want, the bigger it's controlled by the concentration. So if you add more polymer, you're going to get a bigger osmotic pressure difference, and you'll get a stronger depletion force. So the osmotic pressure controls the magnitude. Sorry, the concentration controls the magnitude of the osmotic pressure, and in turn the depletion force. But the length scale, the gap in here, how far apart those particles have to be for this to start to occur, is actually controlled by the size of the polymer, not its concentration. So the length scale is controlled by the size, and then the osmotic pressure, the scale, the magnitude is controlled by the number of polymers in solution. Now, this attraction occurs because you've added polymer. This is an attraction that is actually reversible. So if you cause particles to stick together because you've added polymer, if you then dilute the solution or filter it or break down the polymer with an enzyme or a autolytic photoreaction or an oxidizer and reduce the polymer concentration, you will reduce the depletion interaction and you could actually have the particles pull apart. So depletion attractions kind of, because a lot of times there's an additional, say, a double layer force or maybe there's a little bit of absorbed material there. So they sit in a secondary minimum where they're not completely stuck together, but they're flocculated. And so depletion attractions can actually be reversible. And you do that by diluting them. And so you might have something where you want it to be pumped, or particles where you actually want them in a flocculated state at one point, but when you go to use them and dilute them, you might need them to be dispersed. And so depletion attractions can be very useful in making products that change their stability depending on the concentrations of polymer that are around. So depletion and flocculations are very good for engineering what are called responsive products or complex fluids. And it's just a pretty cool bit of thermodynamics. Change the concentration, the depletion force goes down. All right. So that gets us through how polymers work in surfaces. We've been going for a bit. We just need to go through viscosity, but what I think we'll do is pause it there, and I'll probably upload a part 2 of this lecture and let this process, because I don't want the file size to get too big. So thanks so much for listening to this part, and we'll just pick up on the next slide when we talk about viscosity of solution in the part 2 of the lecture. So I'm gonna stop the recording and I'll just restart the screen capture.